Welcome, ladies and gentlemen, to your Part B of your note guide for section, I actually have forgotten, 7.2. And this is actually a continuation of the first part, and it is still raining outside, not that you care, but I'm just like, obviously I'm doing it all in one great big swooping motion here, these videos. Okay, so this is half-life, and it's an interesting concept, and if you've had chemistry or biology, you have had some experience with the word half-life or what it means. But mathematically speaking, it's the amount of time it takes for a radioactive substance to decay by a half. So if you have 100 grams of something, it's the amount of time that it would take to end up with 50 grams. So how much time does it take to have a half of it left? Because it is half-life, the decay factor will always be 1/2, or again, I kind of like writing it as a decimal, 0.5. Excuse me. The exponent will represent the number of half-lives. So it's so instead of just having your model raised to the x, you're going to have x divided by half-life. And again, so let me just kind of get this straight. The exponent will represent the number of half-lives, and so if you want it actually in terms of how many years, you need to do this x divided by half-life. Otherwise, if you just do it raised to the x, you are finding the number of half-lives, and then you have to calculate the number of years or minutes or whatever. And I'll explain to you that a little bit more closely here. So there's kind of two schools of thoughts on how to do half-life problems, and I'll demo it, I think, towards the end, different way. So whatever works best for you. I do want to say C14 tends to be one that is used with radiocarbon dating. Obviously, if you know anything about dinosaurs or the great woolly mammoths in the Dakotas, they use C14 carbon dating to decide how many years ago they had lived. 5,730 years is how long it takes for half of the carbon to C14 to decay, which is why it's great for carbon dating of very old things. Okay, half-life model, very similar. I don't want you to feel like you have to memorize this because this looks, actually I'm going to do this. Y equals AB to the x is what we're used to. That is the thing you need to know. Y equals AB to the x. The A doesn't change, that's still the initial amount. But the B, like I said, is always going to be a decay factor of 0.5, like half of it still remains. What we do is then we say, hey, you know what, let's get rid of that and say instead that it is 0.5, just to kind of simplify things. And then again, instead of saying x, because that would be the number of half-lives, it's easier for a lot of students to think of it in terms of x over half-life. And again, I'll explain this here in just a moment with an actual example. I find it's easier to understand then. Okay, so let me show you what I'm talking about. So sodium-24 has a half-life of 15 hours, so hugely different than C14, obviously. So you have 18 grams of sample, so let's just make sure we understand this is our A value, our initial amount. So an 18-gram sample is being used. It says write an exponential model for sodium-24 for a half-life. So we have Y, just using this formula here, or model, Y equals 18, because we have 18 grams, times 0.5, because we're dealing with half-life, half of it remains after 15 hours. And this is where I'm saying you go x over 15, because you're dealing with every 15 hours is one half-life, and this will make it much, much more understandable when you find your solution. Okay, so let me show you how that works in an actual problem. So that's the model. Now we can do all sorts of answers with that model. It says how much sodium-24 will remain after 60 hours and also after 3 days. So Y equals 18.5, and because you did this x over 15, you can just throw that hours right in, 60 hours over 15. Because here's the thing, when you think about it, 60, if you take 60 divided by 15, you're talking about 4 half-lives are going to happen in that time frame. So if you don't write it with that x over 15, you're going to have to do more mental computation, and again, that seems to be where students get a little bit confused. So we can tend to teach it the way I'm teaching it right now. What do I do? Yeah, well, you know what? I don't always do it the conventional way. So, okay, so here we go. When we, again, make sure you know how to do this in your calculator, because that's probably the hardest part about this. And so you use your calculator to make sure you're getting this 1.125 grams. So that is how many grams of this substance of sodium 24 after 60 hours. Now 3 days, well, here's the thing. We're using the same model. That's the great thing about a model, is you can use it many times as you need. And here's the thing. You cannot put 3 in for x because 3 is in terms of days, not hours. And of course, we have 15 hours as the number of, or as the half-life. So if you take 3 times that 24, you'll end up with 72 hours in 3 days, and that's over 15. And again, you do a little bit of calculation in your calculator, you end up with 0.65 grams. Yay! Okay, so that is like really the essentials of half-life. You just really need to be okay with this right here, this idea. So it says, and once you have your model, then it's just kind of plugging and chugging. So it says, when will approximately 0.25 grams remain? Well, we put that in for the remaining, or the y value. So 0.25 equals 18.5 raised to the x over 15. Now, this is just like you would probably envision. So let me just, maybe sometimes students don't realize when they need to use graphing to solve things. Anytime the x variable, or the variable, whatever variable you're using, is in the exponent spot, you have no way, you have no ability at this point in your life to be able to solve it algebraically. Again, you use logs to do that, and I have not taught you logs. So this is where you would graph it. So this would be, and again, you could use my shortcut where you divide both sides by 18 and then plug it into your y1, y2, or what I just did there. That was kind of a weird thing. Hold on. But ultimately, you know, this goes into your y1 and this goes into your y2 if you don't want to do that shortcut method that I showed you. And since we've done Desmos and talked about the graphing calculator, I'm going to just assume you at this point in time can put those in, adjust your windows, calculate your intersection, and you would find that your x is equal to 92. So your intersection is 92.55 hours. So that is how long it's going to take in terms of hours to have sodium that's 24 that started at 18 grams drop down to 0.25 grams, which is almost really nothing. And if you want to get fancy, folks, you can figure out how many days and minutes. That's all great. Or days, I'm sorry, and hours. Heck, you can go days, hours, and minutes if you really want to be an overachiever. So I'm just saying this is the same thing. I like days and hours because it's more understandable in your brain. So 3 days, 20.55 hours is when this situation is going to happen. So I like this. This is a better answer, but I wouldn't mark it wrong if you put this here. Unless it says to write it in terms of hours or days and hours. So you just have to read those instructions to make sure that you're doing the right thing. Okay, so let's kind of keep going and see if we're kind of understanding this. It says in example number 5, after 42 days, a 2-gram sample of phosphorus 32 contains only 0.25 grams of isotope. What is the half-life? Of phosphorus 32. So this is really a different type of problem because they're not giving us the half-life. They usually give us the half-life, but we're having to figure it out. Well, we know what's remaining is 0.25, so I'm going to put that over here. 0.25 equals, my initial amount was 2 grams, so I put 2 as the initial amount. I know half-life's decay is 0.5, or the decay factor is 0.5. And what had happened, this is what happened after 42 days. Now I'm putting 42 up here, and I actually want to know, and I'm going to use h as my half-life. So again, I like using variables that kind of help me out, remember things. So this is the model for our situation, and of course you need to solve for h. And this is where you'd put, and again, notice the h is in the exponential spot, so you have no algebraic way of doing this. So this is, again, a graphing one. Maybe we should put stars by ones that we graph, right? So this is your y1, this is your y2, unless you want to do that shortcut thing that I showed you, which is divide both sides by 2, so that you don't have to adjust your windows so much. And again, whether you're using Desmos, again, make sure you can do it in your graphing calculator, but ultimately once you have that down, then I find Desmos easier. But h equals 14 days. And again, I know it's days because this has been sitting there for 42 days. That's our unit. Okay, so that's how you do that. Now, I kind of promised you at the beginning that I would show you maybe just a little bit of a different technique. And so I'm going to do that right now. So I'm going to show you a big old OR. Like, this is another way you can do this kind of problem. You can do this. You can say, hey, you know what? I know this is 0.25 over here, just like what we had on the left side. I know this is 2. That can't change. This is 0.5. But instead of saying this 42 over h thing, I'm just going to say x. I'm just going to say x. And then I'm going to graph it and find the intersection. And when I find the intersection, I'm going to realize that it's x equals 3. Now the problem with this method is, and this is what I do, I told you I kind of go by my own what I do, but you have to realize what you just found is the number of half-lives. So I'm going to write that here. 3 is the number, or 3 half-lives. So that's where you do need to do an additional step if you choose this method. Now it's easier graphing and setting up and all that kind of thing, but you need to understand that you need to actually figure out how many days 3 half-lives is going to be. And so that's where you go 42 divided by 3, and that's going to give you 14 days. So it'll give you the same answer. It's just a hugely different approach to how to do it. So instead of doing the fractional exponent, the 42 over h, or in letter C, the x over 15, you can just use the variable x, but just make sure what you're finding is the number of half-lives, and you're going to have to do some calculations from there. Okay, so this last example, let's just kind of see if we kind of have her down. And I showed you my little thing right here, this, but I won't do that anymore. So if that makes sense to you, that's great. If you want me to show you more examples of it, that's great. That's fine, I'll show you. But teaching-wise, because I do teach the masses, I find that that does confuse more people. It makes absolute sense to me, but that's just how my brain works, and I've just found that the majority of brains do not always work the same way as mine. So, and that's good. Otherwise, it'd be a very dull world. Okay, so in 2016, you find a very old painting in an attic. A piece of the canvas is carbon dated, so this is using that C14 anytime you hear carbon dated. The lab finds 3.8 grams of the original 4 grams of C14 remains. When is it believed that the painting was made? So let's set up a model here. So we know we have 3.8 grams left of the original initial amount of 4 grams. We know the growth rate can't be anything more than 0.5. And again, this up here, I'm going to erase this right here though, because that's in my way. I'm going to use that fractional idea where x is the amount of time over the half-life. So 5,730. Where am I getting that 5,730? Well, way up here, this right here. Okay? And will I give that to you? Absolutely. But I just kind of want to make sure you realize that's definitely the most popular type of half-life calculation. So looking at it, we have to decide, is it a graphing one or is it an algebra one? The x is in the exponent spot, so this is a graphing one. Yay. So again, this one, looking at it, I would definitely divide both sides by 4 and then get in your graphing calculator. But regardless, you're going to put this into your y1, this into your y2. And when you calculate it, you know, I'm going to be completely frank, it's not going to make a difference really if you divide by 4, because you're talking about half-lives of carbon dating, and it's going to be a very large number, so you're going to have to really adjust windows. Because of that, that is the reason why I do my little thing like this right here, because then I could just find the number of half-lives and then figure it out of that 5,730. But anyway, when you calculate x, when you find that intersection, and you're going to have to mess with those windows quite a bit, you're going to, and again, this is a very old painting, so we obviously know it's many years ago. So keep adjusting the windows until you get 424.02 years as your intersection. And so you're talking about, just to kind of give you an idea of what I'm referring to here, is that your x-axis, the windows, have to be, and you could say 0 for the x-min. So let me do this better. So your x-min can be 0 because obviously you can't be less than 0 time. But your x-max has to be like 450 at the minimum to be able to see where that intersection is happening. So it's again, it takes a little time to adjust those windows for these kind of problems, and I just kind of wanted to make sure that you realize that. Now, it says, when is it believed that the painting was made? So this is clearly talking about a year in life, right? So we're talking about 424 years back in time. So you're going to have to interpret this kind of problem. So if we're in 2017 right now, and if I use this video next year, the year after, whatever, obviously adjust this date to whatever date we are in, minus 424 years. Of course, I can say 0.02, but you know what? Let's not. This is ancient, right? So let's not worry about that 0.02 years. So you're talking about 1593 AD. That's a big deal. Yeah, that's pretty old painting. So that is, in a nutshell, how you do half-lives. And again, super helpful in chemistry, in biology, in obviously ancient civilizations, all that kind of good stuff. But anyway, and use whatever technique works for you. Again, you're going to have to get proficient with those graphing calculators. Desmos, of course, is an amazing tool. Something that wouldn't be bad while you're playing with the graphing calculators to maybe do it in Desmos to get the answer. And so you can kind of get used to adjusting those windows. So I know you guys can get it into your Y1, Y2. I know you can use that intersection button, but boy, those windows you're going to have to play around with to see the graph that you need to see. Okay, well, thank you for tuning in. And if you have any questions, you can ask me when we see each other face to face. Take care.